Hey there, this is our module walkthrough for analysis of covariance. As usual, start off with the README file for analysis of covariance. Here we have the assigned readings for the week. We'll look at Chapter 6 on analysis of covariance in the Tabachnik and Fidel book. I've also posted some notes where I've summarized the readings and summarized some of the chapters from some other ANCOVA textbooks. And then I also have a zip file of some other helpful information that I found on analysis of covariance. There's also a link to the assignment and quiz here. You'll also find a copy of my notes here on the main module page for ANCOVA. We'll look at these briefly in a minute. You can download the zip file of your non-textbook readings here. This is just a neat web link that gives you some of the formulas for calculating different effect sizes in analysis of covariance. So if you're just wondering how the partial eta squared is computed, you can see the formulas there. There's also several resources for running an analysis of covariance and SPSS. I've made a walkthrough video here, so you can link to it on should be able to link to YouTube. I don't know why they're not opening in Canvas, but you can see the video there. Here's the different steps for running analysis of covariance in SPSS. You can follow along, examine the homogeneity regression assumption. You click on Analyze, General Linear Model, Univariate, and it kind of walks you through, what the different steps that you would do. So you can, that's a good guide to keep handy when you're practicing through the example and working on the homework. Here is my annotated example in SPSS, and I go through this in the video, but you can see here's the problem. You can practice typing in the data into SPSS. I've also given you at the end of the example, the average problem solving score in the sample is 149.76. So when you get these data entered into SPSS, you can just run some descriptive statistics on problem solving and creativity, just to make sure you didn't. And as long as you're getting means the same as what I've gotten within rounding, then you entered your data in correctly. It's just a way to catch that you've entered it. Also notice that all the analyses are completely annotated. Here's some preliminary analyses you can run. Here's output examining the homogeneity regression assumption, what we're looking for, how we would interpret it. And so I'll explain this in more detail in the ANCOVA and SPSS video here. Here's the dataset file. Here's a SPSS syntax file. So if you want to see the syntax that you can actually run these, some of the commands are actually a lot easier to run in syntax than they are through the drop-down menus. So that might interest you. And I've also written a results section for this example, so you can see here is an example of results section, how you might write up the results from analysis of covariance. So those are all the resources on Canvas. There's also a link to here, the assignment and quiz for the week. You can say we can view you can notice that the assignment is set up pretty much the exact same way the example is. It's taking a minute to load. And you can see the quiz is linked here too. Did it ever show up? Let's see. Let me know if you're having troubles actually opening it on Canvas, and I'm trying to reload it if something's not working. We'll just talk a little bit. I'm just kind of run through some of the notes that I've made on ANCOVA. I'm not going to read all these to you. I'm just going to kind of skim through it. You can read through it. If you have questions, always email me or post to the message board. Just get a general idea. Analysis of covariance is kind of an extension of the ANCOVA models that we've talked about, where we're including both a categorical variable and a continuous variable. Typically, the continuous variable including we call it as our covariate. Typically, in analysis of covariance, the categorical independent variable is our main variable of interest, and the covariate, which is typically continuous but doesn't have to be, is an extraneous variable that we're wanting to control for, to kind of take into account. We want to take into account variation on this covariate to then examine differences on our independent variable, our main variable of interest. You can see, kind of one of the advantages of using an analysis of covariance is this reduction in error variance. That's what this is trying to show. This is all the variability in the outcome. Our main independent variable will eat up some of the variance. The covariate will eat up some of the or explain some of that variance rather, and then your error variance is then reduced. When we talk about ANCOVA, you'll hear people talk about it statistically controls for the effects of the covariate. When we're talking about controlling for the covariate, we mean that we're taking away variance that's associated with the covariate and then testing for group differences on that dependent variable. So what we're saying is, if our groups were equal on our covariate, would we see differences between these groups on the dependent variable? So you can see here's an example here. We want to know whether 3 different teaching strategies, if one of them was more effective at increasing students' math achievement. So our main independent variable of interest here are the different teaching strategies. And so we also know that, students' IQs would be related with math achievement. We would typically expect students with higher IQs will have higher math achievement. So we might want to take into account intelligence in some way, and then see, controlling for intelligence, or if everybody was equal in their IQ, would we see differences in these different teaching strategies? Notice here that, we want our covariate to be correlated, to be related with our outcome. And we also don't want our covariate, or if we have multiple covariates, we don't want them to be related among each other. We also want to see low correlations between our covariate and our independent variables here. In this case, if we were randomly assigning people to different teaching strategies, then, by the design of the study, IQ shouldn't be correlated with teaching strategy. They should be, roughly distributed, equally distributed among the different groups. In experimental designs, analysis of covariance is a great way to help reduce the error variance. Using non-experimental designs, analysis of covariance gets a little more tricky because we have to consider, one, is our covariate related to our independent variable, and whether adjustments on the covariate is something that's could actually occur in real life. Well, it kind of gets into our next thing here, using ANCOVA with intact groups. If you start Googling analysis of covariance, you'll see a lot of different arguments out there about, some people are completely against using an analysis of covariance and non-experimental designs, or in places where we would have actual intact groups where we're not randomly assigning participants to groups. Some people will argue against using analysis of covariance for that. I'm not that as strict on that argument. And it's mainly an argument that ANCOVA gives us test of differences as if the groups had been equivalent on the covariate at the onset of the study. And so in this case, you would want to consider whether groups that are equal in the covariate would actually exist whether they actually exist in the real world. You'll see people making claims about ANCOVA that ANCOVA statistically equates groups, or that analysis of covariance completely eliminates bias in the study, and neither one of those claims are actually true. There's a good discussion of using ANCOVA in intact groups in this Pitchers and Stevens text. So if you want to check out that citation, you can read about this issue more if you want. We've touched on this issue a little bit, the importance of choosing a covariate. The Topashik and Fidel book, the readings in there, they talk a good deal about what would be the ideal covariate. We think about the ideal covariate would be one that is, significantly correlated with the dependent variable. We would also want to have a substantial correlation. And we would want our covariates to have low correlations among themselves and low correlations with other independent variables. A good way to assess this is just to run some bivariate correlations on the variables used in your study. It's also important that the covariate is measured before the independent variable or the treatment variable to avoid confounding the treatment effects with changes on the covariate. I'd also found this in this from this citation here. He gives an inequality here to kind of judge the number of covariates. So if you're going to use more than one covariate, you can kind of use this inequality here. I have an example here. Say we had 60 participants, and we had our independent variable had 3 groups. We could fill out this inequality here. 3 minus 1 is 2. Divided by 60. Multiply both sides by 60. Subtract 2 here. So we'd want less than 4 covariates. So in this study design where we have our independent variable has 3 levels, we have 60 participants, we could have at most 3 covariates for the model. The argument is the ratio is greater than 0.1, and the estimates of the means are kind of unstable. You can see sort of the null and alternative hypotheses listed here. Notice it has a little prime tick above these, because just indicating that these are adjusted means. So the null hypothesis, which is a typical hypothesis of no difference, is that there's no difference between the adjusted means of the groups, against the alternative hypothesis that at least some of the adjusted means are different. The assumptions in analysis of covariance, we make all the same assumptions that we made in ANOVA. So we have the assumption of independence, our homogeneity of variance assumption, and our normality assumption. And we also make 3 additional assumptions. So we have all the assumptions of ANOVA plus this linearity assumption. We want to say that the relationship between the covariate and the dependent variable is linear. If the relationship is nonlinear, then the adjustment ANCOVA is making isn't correct. And so we can assess this. We could just graph our outcome on the y-axis and the covariate on the x-axis, and just assess kind of visually the linearity assumption there. The homogeneity of regression, or you might hear it homogeneity of regression slopes, is basically an interaction effect. It's saying that there's not an interaction effect between the independent variable and the covariate. So it's saying that the impact of the covariate on the outcome is the same for each level of the independent variables. So what that would mean is, if we were graphing, that would mean that each group, that the regression line for the between the covariate and the outcome would be parallel in each one of the groups. Testing for homogeneity of regression is sort of a prerequisite to conduct an analysis of covariance. If we fail this test, then we don't need to do the analysis of covariance. So we're going to check this. If basically we're just going to build an ANOVA model with that includes our independent variable, our covariate, and an interaction term between the independent variable and covariate. If that interaction term is statistically significant, then we have violated this assumption and we should stop the analysis and not do an analysis of covariance. If the interaction term is not statistically significant, then we have evidence here that this assumption is satisfied, and we can continue on with the analysis of covariance. We also assume that our covariate are measured without error. This is probably violated usually to some extent in the behavioral social sciences, and violations of this assumption tend to be more severe in non-experimental designs. The general recommendation is, if you're using like a well-established measure, maybe like IQ or something, or a standardized test score, like I said, that's well established, you'll probably have an estimate of the reliability for that measure, and you'd usually probably want to report that in your write-up as well. Chapachnik and Vidal chapter talk about some other important data considerations you can kind of read through here. In this section here, I've tried to explain this idea of what's going on with the adjusted means, and that's what I'm doing here. So we have 2 groups here. We have a treatment group and a control group. So this diagram sort of illustrates both the homogeneity of regression assumption. That's what these parallel lines would indicate, the homogeneity of regression. And then this kind of shows you that idea of the adjusted means. So if we look here at our, this is our P, this point P here would represent the point on this graph that, so be the average age and the average earnings for people in the treatment group. So the idea here is, look, we have earnings graphed on our y-axis, age graphed on our x-axis. In this example, age often explains differences in earning. Typically the older you are, the more you earn. So if we're looking at differences between this treatment and control group, we might want to take into account the age of the participants, because maybe those, if everybody in the treatment group just happened to be older than those in this control group, age might actually then be explaining the differences we're seeing in earning. So here, what we're looking, this point P then represents the average earnings and the average age for those in the treatment groups. This point Q here then represents the average earnings and the average age for those in the control group. So you can see the difference between the just the raw average here. This would be our unadjusted differences, earning differences. And so what's happening in the analysis of covariance is it's then adjusting our group means, pulling them towards the overall average. This is the overall average age score. So it's saying then what would then be the average earnings if everyone was the same age. And so what it's going to do then is it's going to pull then this average, it's going to just pull down the regression line, the average for the group mean for our treatment group. So point P is going to fall down the regression line here. It's going to adjust it back towards the grand mean. And so then we would have, then here would be our adjusted earnings score for, or adjusted earnings mean for the treatment group. And then for the control group, it's going to also adjust them towards the grand mean. So some groups get adjusted up, some groups get adjusted down, both towards the grand mean here. And so in analysis of covariance then, so we're adjusting groups based on the average covariate, and then we're assessing differences between these adjusted means. So these are then our adjusted mean differences. So this is saying this would be the expected difference in earnings if everyone in both groups were the same age. So that's kind of the idea of the adjusted means. And if you see how these lines are parallel and we're adjusting up and down the line, this is the whole idea of the homogeneity of regression that the groups have, that the impact of the covariate age is the same in each group. If it's not, then this adjustment that we're making isn't correct. If this assumption isn't satisfied. So you can read, try to explain what's going on in this little paragraph here, but that's kind of an overview. Tomatic and Fidel also give a lot of different alternatives to analysis of covariance, especially if you violate like the homogeneity regression assumption, some different strategies you could possibly implement. So there are different effect sizes we can also get for analysis of covariance. So we have our eta squared statistics, which are our variance explained statistics. And SPSS will report several of these in there. All of these type statistics, you'll hear them called eta squared, partial eta squared, R squared, adjusted R squared. Really measure how much variance in the dependent variable can be attributed to or explained by the changes in the independent variable of interest. So SPSS will report a partial eta squared for both the independent variable and the covariate. And these both represent sort of the strength of relationship for each one of those variables. So for like the independent variable, it represents the strength of association between the independent variable and the outcome holding constant scores on the covariate. SPSS will also report, they call it R squared in the table, and an adjusted R squared. And so these would be variance explained effect sizes for the entire model. So say the adjusted R square value was 0.43. That would say that around 43% of the variance in the outcome can be explained by both the independent variable and the covariate. So the R squared and adjusted R squared that it's reporting is the proportion of variance explained by everything that's in that model. You can also calculate Cohen's D's for different pairwise differences. So if we have, if our independent variable has more than 2 levels and we end up doing a post hoc procedure, and we're looking at differences between group 1 and 2, differences between groups 1 and 3, 2 and 3, we could calculate a standardized mean difference, or what we call a Cohen's D value for each one of those. So, this is really a distance measure. It represents the magnitude of difference between the 2 groups. It basically turns that mean difference into standard deviation units. So it's saying that group 1 and group 3 differ by 0.5 standard deviations. And then I'll show you in the SPSS walkthrough video. But Peters and Stevens recommend dividing the mean difference by the mean square error term from a one-way ANOVA with just the IV. So the argument is the error term in the ANCOVA is reduced too much, that the Cohen's D values are inflated, basically using it. So it says to just run another one-way ANOVA on the outcome with just the independent variable, and then use that mean square error term as the denominator in your Cohen's D calculations. So we kind of mentioned this, if your independent variable has more than 2 levels, you need to do a post hoc test or some type of contrast. SPSS only offers the LSD, the least significant difference, which is no adjustment at all, a Bonferroni or a SADAC post hoc for you to choose from. And I think in the example, I walked through a Bonferroni adjustment. One of the ratings here is from Miller and Chapman. It's, common misunderstandings of ANCOVA, and you can kind of get an idea and sort of their arguments for and against using analysis of covariance, especially some of the pitfalls of using ANCOVA with intact groups or non-experimental groups. Here's also just an example ANCOVA from the literature. You can see just how kind of they've written up their results. Here's a citation, little abstract from the study in their results section. Here are different citations that I cited in the notes, and then I tried to provide you some helpful videos. Here's a couple introductory videos here on analysis of covariance. Here's kind of a walkthrough of some of the assumptions, and here's a kind of a 7-part series of doing analysis of covariance in SPSS if you're interested in that. So that was kind of my quick module walkthrough and brief lecture. As always, if you have questions or concerns, please shoot me an email or post to the message board. Thank you.